So going here. This is the last section of the last lecture. Are you excited? I know. Nobody's going to miss this class, but I'll miss all of you. Maybe. Some of you. No, sorry. No, they're a lost cause. They're a lost cause. They're just a lost cause. I get it. I gave out quizzes. They're a lost cause. I will tell you before I get to the teaching evaluation part. Let me tell you, I want you to be. I'd love to know your feedback more than just the numbers. And of course, our beautiful form has no spot for like your written evaluation. So if you could, when you get this right on the back, suggestions for improvements, things you like, things you didn't like. I had one person once draw a fire-breathing dragon and said class was effing awesome. Actually put it in the word out there. That means a lot to me. The numbers themselves, to me, I don't get anything out of it. And not only that, like the university, they don't care. So let me make the class better with what you write. So I say they don't care, but honestly, nobody's getting raises and teaching that wasn't evaluated anyway, so it sucks. Not our best thing. Not our best bet. But that being said, how about we talk about finite mixture models? Sounds pretty fancy. Have you heard of finite mixture models? Yeah. Latent class models? Latent class analysis, are those? Few of you? All right. Finite mixture models are ways of doing clustering with likelihoods. Remember clustering, the key word there? We have a bunch of people or a bunch of observations. We don't know how many groups we have. We don't even know if we have groups, but we'll try to find out. So what we're going to do is come up with a finite mixture model that try to figure out how to put people into clusters or into classes. The word finite means we're going to have countably many, right? A set of them, things that we, usually a small number. Mixture means that the distribution of the data, the marginal distribution of the data, comes from a mixture of observations from different classes. And in fact, it's a proportional allotment, right? So unlike k-means, one of the things that finite mixture models do is it allows each observation to be proportionally allotted to each class, right? So it's, you may have a person, you may have some, like in the flower data, you'll see we have this one flower where every observation from it got certainly into that flower. Where those overlapping flowers, you had some of the observations in the middle, they'd be like 50, or between those two would be 50-50. Maybe it's more like, 50-50 and 0, right? They're certainly not in the one class, but they're 50-50 with the other. So you start to see a proportional allotment, how this works. So finite mixture models use likelihoods from statistical distributions to determine class membership. So a likelihood, or a PDF, is a similarity, as we talked about already. And you can think about how this might proceed. In fact, I'll just describe it for you. Conceptually, like k-means, let's start off by taking all of our people. Let's imagine we have 150 flowers. We're going to come up with 3 classes. We're going to randomly just put a flower in each class. There we go. So now we have 50 flowers in class 1, 50 flowers in class 2, 50 flowers in class 3. What we then do is we calculate, using maximum likelihood, the parameters of the values in the class. So for today's class, we're using multivariate normal. It's like saying, okay, now I've got everybody in class 1. Let's use Levon or whatever else and estimate the mean vector and the covariance matrix. All right, so now we've got mean vector and covariance matrix and a likelihood value for it. Same thing with mean vector and covariance for class 2. Same thing for class 3. So the next step then would be to go for each person and then using that mean vector and covariance matrix for each class, calculate their likelihood for each. Right? Not a distance, a similarity. Right? So it says, okay, for the flower 1, using class 1's mean vector and covariance matrix and the multivariate normal likelihood function, how likely is this flower in this class? And same thing for class 2 and same thing for class 3. And from that, those 3 likelihoods, we can come up with a probability that a flower belongs to each of those classes. And so now that probability is used to weight the membership of that flower into each class as we move forward. So next thing we do is we go and then go back to our classes and say, now you know that these flowers are no longer all in one. This first flower is proportionally in this class and proportionally these others. Now calculate a mean vector and covariance matrix using the weighted portion of each flower. Right? Each flower gets weighted by the probability into each class. And now we calculate a brand new mean vector and covariance matrix. So that process repeats itself over and over and over and over. And actually, that thing is called the EM algorithm, for anybody who's ever heard of that before. Expectation maximization. That's how it works. So the cool thing about finite mixture models, they go back there. Some of the earliest papers, the earliest paper I ever saw about this, and yet again, it comes from agriculture. Pearson, the guy who gave you your favorite correlation. The Pearson in the Pearson product moment correlation. I hate that. Anyway, has a paper in 1890 that talks about the size of crabs. I kid you not. Right? And I'm just going to flip to it. Let me Google it. This is always dangerous. Pearson crab data. Carl Pearson's crab data. There we go. We might be able to see some images for it too. There we go. Yes, Devane?
Sorry. Things happen.
Yeah. So here, the data themselves of this red line, and it turned out he fit a mixture model to this. He basically said, I have these data. There's some measurement. No, it's the ratio of the forehead of a crab to its body length. Evidently, that's a biologically meaningful thing. And it turns out, it says right here, one of the earliest uses of finite mixture models. What he said was, these data, they're not normal. If you look at it, right? They're sort of skewed. And so what he had surmised was that there are either different species of crabs or perhaps like there's a biological difference in crabs as you go forward, and tried to figure out essentially what were the underlying species of crabs that might give rise to this red line of data. So here there would be three, there's single normal. If you just fit a univariate normal without classes to it, you get this dashed line, which doesn't quite fit the red line. If you fit a two-class model, you get a normal distribution here and a normal distribution there. And once you sort of aggregate by how likely these two distributions are, you get the red line, or much closer to the red line itself of the data. So what this is an example. The year of this example is 1890. And this is how old this is. The problem is doing this is exceedingly difficult, and it involves computation. Right? This was the problem. Did I mention the hardest homework problem I ever had in grad school to you? I probably did. It was the professor who said, I'm giving you, I think it was the weights or maybe it was the heights of the people in my intro stat class this year. I want you to come up with the mean for men and the mean for women, assuming the variances were the same and the mean for men is higher than the mean for women. Oh, by the way, I forgot to collect who was a man and who was a woman. Right? So that was the way I learned finite mixture models in grad school. And I don't know, go program it or whatever else. Good luck, right? That was it. But that was essentially what this is happening. If we had these, maybe these were male and female crabs. I don't know what the difference of this are. I'm not as familiar with this paper as others. But we could say, if we have these two classes, we could say, oh, look at that. The mean for this one is right here. The mean for that one is right there. Furthermore, if we wanted to classify crabs as we went forward, if we had this ratio, one of these two classes would be more likely for every crab. Right? Once we get to the one with the peak. So that's a finite mixture model for you. Right? It tries to fit multiple classes to the data, and ultimately it's trying to recover what the original data looked like. This is a univariate example. We have one observation. In our flower data, we have 4. And all sorts of funky things happen when we go from 1 to 4. So the names that these have come up with, though, is latent class analysis. There was a book by Lazarsfeld and Henry, 1968. Awesome book. It dictated a few names for it. Latent class analysis really gets attributed to Lazarsfeld, although it happened before this book. That's a finite mixture model where we have binary data. Right? So maybe we have test items for each person, whether or not they answered each item correctly or incorrectly. And each of our classes makes it so that for the items within the class, all the responses are independent. So this conditional independence upon class. So it's kind of a restrictive assumption, but it does happen. That's what we call a latent class analysis model. Lazarsfeld and Henry kind of switched that up a little bit. If you had continuous data or normal data, but they were independent within class, in the book they define that as a latent profile analysis. The same type of idea. The difference between the two comes from the difference in likelihoods. For binary data, we might use a Bernoulli likelihood. For continuous data, we might use a Gaussian. It still fits in the same framework. More recently, we get into things like factor mixture models. So if you have a CFA model for your data, and you want to figure out whether or not you have multiple classes, you might use a factor mixture model. Basically, it's saying which group of people has this one type of factor structure, and which group of people has a different type of factor structure. In any of these, the programs for it are, there've got to be better packages than when I looked, but I've always felt my bias toward R is that the packages are very limited to do in R. If you want to do this well, the packages I would recommend are mclust, or Latent Gold is another one. I don't know if you've seen or heard about those fun times with mixture models. But if you're interested in more of that, I can send me an email. I can point in the right direction. They get all sorts of things. What we're going to see today is really naive compared to what you can do. What you learned in this class is that every model has a likelihood, right? So what I'm going to tell you about finite mixture models is if you have a likelihood, meaning if you have any model, you can put it in a finite mixture model and get a class out of it. Right? That's how cool these things are, right? How does it work? This is the marginal likelihood of the data. I'm trying to unpack it. F of x given c, that's your model for a given class. Right? So if we only had one class, this thing would just be your model's likelihood. Now, if you have more than one class, this is essentially each class has its own model, right? So if you have a regression analysis, right, you have x predicting y, you could go put it in a latent class model, right, Megan? Or finite mixture model. Megan did this. This is the thing she did. I was going to tell her, have her talk, but I'll spare her. We had two classes. Regression line for class 1, regression line for class 2. Sure enough, the regression lines were different, right? Well, the regression line for class 1, it has its likelihood. That likelihood is weighted by the proportion of observations that are in that class. That's what this eta term is. Well, class 2 has its own regression line. So it has its own likelihood. It's weighted by the proportion of classes that are in it. So when you go and weight each likelihood by the proportion of observations in it, that is the mixture that's happening. So this eta c is called the mixing proportion. That's where the mixture gets its name. You've got a mix of people in class 1 or people in class 2. And the thing about it is, people aren't necessarily tied to all one class in these analyses, right? If you've got people who are sort of 50-50 for a two-class analysis, what it will do is it'll take half of a person's data and put it in class 1, and take the other half and put it in class 2. So it's not overweighting each person based on how certain you are that they are in each class. So the mixture model itself is a cool idea. Like any exploratory analysis, it will suffer from its own things. I'll talk about that in just a bit. But if you're getting excited about this, you're like every other researcher who had M+ about 10 years ago, which was, I have data. Can I put it in a mixture? Right? So the answer is yes, you can. The question should be, should you? Or better yet, did you get anything out of it that made sense, that actually was truth or more than noise? The problem with these is that you could come up with lots of noisy data. And if I were to flip back, just to keep this to it. So there's our data, right? This is our data. And Pearson came along and thought, I got class 1 and class 2. And maybe he knew something that we don't. But there's no way to differentiate class 1 and class 2 from, this is just the distribution of the data. Not everything is normal, right? So that's the problem with the mixture model. is that you get these wonderfully precise likelihoods that talk about the distribution of data, but if the data don't follow them, guess what you're going to get? Multiple classes, whether or not they actually should be there. Right? So that's kind of the pitfall of it. I don't want to ruin it for everybody just yet. So R has several packages for mixtures. We're going to do a mixture of multivariate normal variables because we focused on multivariate normal in this class. What we're going to try to do is figure out the number of classes in our flower data using only the 4 measurements. And one of the packages we can use is mclust. Mclust is its name, and when you load it up, it makes this beautiful Courier New Art line printer graphics. This is so 1970, right? This is like not even dot matrix level. Even like, by the way, even like the rental car companies are going away from those dot matrix things. That's amazing. That used to be the thing that I think slowed down the rental line more than anything else. Anyway, so what we're going to do is we're going to figure out for each class, we're going to get a likelihood. That likelihood is going to be the log of this from each person. Right? So it's the sum of the log of this f. And just like you saw in maximum likelihood, this is actually the way we estimate this is what we call marginal maximum likelihood. We're estimating the likelihood of the data once we've marginalized across all the classes. That likelihood we can treat just like any other likelihood. So when we have multiple models, we can do model comparisons. Right? The classes are actually nested within each other, but the likelihood ratio test gets a little wonky because the boundary of the classes, or the values to make a 2-class solution, for instance, into a 1 sets a whole bunch of parameters to their boundaries. So the statistic itself is a little weird. But what we can do is use an information criterion to figure out which class is best. And so this mclust package in R with the mclust BIC function, it will fit a ton of these latent class models. This is the number of classes, 1 through 9. This is the BIC for each. We're trying to pick the one with the smallest BIC. That would look like this one right here, 2, whatever EII stands for. There's a whole bunch of permutations. Those involve assumptions about the covariance matrix, right? Whether or not it has the same variance in the diagonal, same variance, the same covariance, no covariance, all of it makes a difference. In theory, this is just it's kind of the shotgun approach to modeling. There's no real reason for any of these. In fact, knowing these data the way I do, what's really happening is that 2 of the classes have very similar covariance matrices. 1 class is different than that. So actually none of these is really appropriate. But once you get that though, here's output. You can have it give you a summary of the 3 classes. This is a separate model I ran. Gives you a log likelihood, gives you the BIC. It comes up with another information. I don't know that one. It tries to tell you the mixing probabilities. That is the proportion of flowers in each class. You see 33, 30, and 36% in each. It even gives you a plot. These are the 4 variables. What you see within the plot is the classes overlaid with our little sphere. That's a centroid. That is like a contour plot of our multivariate normal, talking about likelihood. By the way, remember the eigenvalues, eigenvectors last time? And we talked about how that sort of took a group and shifted it. Those eigenvalues and eigenvectors give you the direction and width of each of those stems in these, if you ever wanted to draw them yourself. Thankfully, R does it for us, but where it gets it from are those eigenvalues and eigenvectors. Some of the fun math that goes behind it. So, we have 3 classes. Each class has a different mean vector. So here it gives us each of the means for each of the variables. Each class has a different variance-covariance matrix. And this is, I asked it for a specific difference in each of these for what we see. And now we see our plot. All right, so now we knew the classes going in, well, we knew there were 3 types of flowers. We get something that looks like a good separation. This blue flower the red and the green are the things that we see. Now, how it decides to color up each flower is that we could go into the output a little bit more. I didn't, but we could have. And each flower now gets 3 probabilities. Those probabilities sum up to 1. Right? The probabilities are found using Bayes' theorem. Sometimes we call them posterior probabilities. But then the question becomes, how do we assign each flower to each class? So here's an interesting thing. This green overlap, you see the greens, those are the flowers that have the highest probability for the green class. And you'll see they overlap quite a bit with the red. But you'll note the probability, this is just 2 of the variables. It's only telling you a little bit of the story. The classification is based on all 4. So on some pairs of variables, there's very little overlap, and on some there's quite a bit, which is what we would expect with species of flowers, but maybe not with other things. So how do we go and try to validate this result? Well, we don't get a lot from this output, but one of the things we could take a look at is whether or not there's a significant difference between these values of means for each of these between the classes, right? So sepal width, for instance, between class 2 and class 3 have means that are very close together. Right? Is that a statistically significant difference? I don't know. Don't know the answer. And that's the problem with this type of analysis. So how are we doing? Yay, fun, right? Not really. You're not. This is not homework, right? This is not test. This is not quiz. This is just for your information. You want what else can I give you about this for your information? All right, Megan, I'm going to make you talk. You have a question?
What if, for one of the classes, you didn't have enough of the sample to detect it?
Like if it, with probability 0 or something like that?
Yep.
It would try to detect it. You may get really wonky values for the parameters with it, right? You might see like 0 variances, or you might see means that make no sense, and you just have nobody classify that. And the reason for that is to classify it's like a weighted variable analysis within each class, essentially. If there's nobody in it, that means its sample size is so small that it's trying to find these parameters. They could probably be anything. Like the likelihood isn't going to really be very different for them. So you can do it. It does happen from time to time. You just get really crazy results for some of the parameters. Sort of an indication that class doesn't exist. It's one thing, yeah, actually, if we were doing all this by hand, fitting 9 models, what we would see probably when we got to 4, or maybe even 5, is that there would be classes that have probabilities very close to 0, or proportions of observations that are very close to 0. Other questions? So Megan, why did you use this? Why did you use mixture models? What did you do with your mixture model?
No.
No, you don't want it? All right, I'll tell
Okay.
you. I'll save Megan. Megan's my advisee, and I'm trying to find research that's quickly doable, compartmentalized, quickly doable. And that's like, I've had this idea for a while. It sort of applies to some of the other things I'm doing, like sports, right, Jake? And so we did a regression. We generated data. We generated data where we had one outcome, and we predicted it by a continuous variable, and then a categorical variable, and then the interaction between the two. You've seen this like all year long, right? But what we did in the analysis with the regression with one class, we dropped the categorical variable. So it just was x predicting y. When you have x predicting y, but you forgot about putting z, or the interaction of x and z, what happens to your regression analysis in terms of the parameters? If x and z are correlated, they are biased. There's the dreaded omitted variable bias. It comes up in different terms for different fields, but if you've ever had control variables, that's what you're controlling for. Right? It's like saying, oh yeah, I did this study, I collected x and y, I've got this great regression, I didn't collect z. your x and y slope will be biased, most likely, if x and z are correlated. So we put, z was this two-category thing, and we put these data into a mixture model. I wanted to see if we could find out the unbiased version of the slope between x and y using a mixture model, right? Or better yet, come up with a different type of slope. Because the other thing we could do, anyway, we put two classes in. We had two regressions, class 1 regression line, class 2 regression line. And wouldn't you know it, what did we find? It fit. And we found the unbiased slope. We basically said, oh yeah, there's the slope we were looking for. Now we knew the data going in.
The interaction.
What about the interaction?
We didn't have the interaction.
We did.
Did we?
Yeah, because we have x have a different slope in each class. That is by definition the interaction. And see, that's the mistake I make too. That's an interaction. I've given you 4 quizzes on interactions in like 4 homework. That's exactly it. So we had it. We just had to we didn't have it in the interaction form. We had it in the submodel form. I'm not trying to pick on you. This is the hard part about interactions, right? So actually, you can trick out mixture models to do all sorts of things. I feel like you can trick them out to deal with omitted variables. The other thing we could do, if we would have looked at the data, right? If we had this mixture model and maybe class 1 looked like this, and class 2 looked like that, if we averaged over them or if we marginalized over it, we might actually get an effect that looks like this or something along those lines. So we could come up with that. If we had more than 2 classes, we might even see some weird effect that looked like this. A nonlinear trend, right? So there's all sorts of things these class models can do to give you where you're not focusing on class 1 versus class 2 specifically, but you can hijack the classes to give you better results to your data or better predictions for your data as you move forward, right? So that's where I'm at with most of these. What do you think? How many of you want to do mixtures? My diagnostic model class next fall is mixtures, but they're confirmatory versions. Hooray. What are the problems with mixtures? That's not the right one. They're exploratory. Oh, I hate that. So that means, by the way, my slide said 2 R's. I realized this before I came to class when I was looking these over. Spurious, 1 R, not 2. Sorry for the typo. One of the millions that you've seen from me this year. But the exploratory uses of mixtures are often suspect as nearly anything can bring about the addition of a model of another class. So for instance, in our data, right here, we assumed each of these classes had an unstructured covariance matrix. So we basically fit as many parameters as a multivariate normal would let us for each of these classes. So in this regard, what could cause this to go wrong? Well, if our data weren't actually multivariate normal, if there was some skewness or some kurtosis, if we didn't meet the assumptions of the data, the only way this type of analysis can remedy it is to bring about another class. It'll be like, oh, the data don't work. Let me bring about another class. Oh, the model didn't fit. Let me bring about another class. All these models that you see here have different levels of assumptions on that mean vector covariance matrix. Just like we were talking about in class this year with MANOVA versus repeated measures ANOVA versus whatever mixed model would give us. Those are different levels of assumptions on covariance matrices. The one that you saw in the last slide with the unstructured covariance matrix was like MANOVA. If one of these goes, actually one of them does, it does the compound symmetry. I can't remember which one it is. There's a spherical thing involved in it. That's not accurate. But what you'll find with it is that the only way it remedies things is to bring about another class. So pretty much anything that goes wrong, anything that you get wrong with the likelihood or the assumptions of the model, the only way it fixes it is to bring about another class, even if no class exists. Let me give you another example. This paper that I was a part of in Journal of Educational Measurement. I think that's where it is. Maybe. I don't know. Yeah, I think it's JM. That's where I'm editing now. Huh. Anyway, maybe APM. It's not like I have a lot of papers. I should know this. Anyway, the paper started like this. I had a postdoc at Georgia, and she was working with a person who really loved mixture IRT models. So those of you who've taken item response theory, it's like factor analysis with categorical data for those of you who haven't. Those of you who have, I'm looking at my students, you know who you are. Basically, it's saying, do I have different classes of people in my data? And so what the mixture IRT model will give you is different item parameters for each class. And the way a lot of people like to use this thing are the different strategies people are taking in my test, which, by the way, is bullshit. But I can't even say BS. I actually have to say bullshit on that one, right? So she came to me and said, look at this. I got 3 classes of a mixture of one of the most limited IRT models there is. What's called a Roche model. There's 1 parameter to it. I've got these data. I found 3 classes. There's all these 3 strategies. And I'm like, hey, I said it. Bullshit. She's like, what? I'm like, oh. So the data came from the state of Florida. That's BS too. But the state of Florida, anyone from Florida, I would love, like, my dream job is in Gainesville. I know that sounds terrible. Apart from KU, rock chalk. But if I could work in Gainesville, I would. I may be working there alone with the swamp, but just anyway. The data came from a testing program that made sure, or tried to make sure, all the items fit a more complicated IRT model, one with 3 parameters versus 1. And so what we end up getting, if you look at the data themselves, if you were to go and look at in IRT, if we have this latent variable that's a factor we call theta, and each item we have this curve to that talks about the probability someone answers the item right based on how much ability or have this factor they have. And when you looked at this from a Roche model, it would look like that. If you looked at the 3PL, it would probably look more like this, right? But when you did the mixture Roche model and you aggregated or you marginalized across the classes to come up with what this would look like, guess what it looked like? It looked like the 3PL, which is the testing program it came from. So it generated this idea for a simulation study. It thought, okay, there's a bunch of people doing mixture Roche models, including one of my biggest adversaries in the field. And we always like to take shots at each other. So I thought maybe we could take a shot at this guy because I could weaken the mixture Roche model a little bit indirectly. Not that it matters. Point being, about the science of it. A lot of people are doing mixture Roche models, coming with all these interpretations for classes that aren't there. How many items needed to look like this 3PL for an additional class to come out, right? So we generated data with no classes to it, and we generated 30 items, I think, in the study, and it was shown that all we needed were 2 items to be 3PL, 2 out of 30, and the mixture Roche model would pop out another class. There you go. Here's your next group of people. Right? So that's the sensitivity of mixture models for exploratory analyses is extreme. Right? That's the danger of it. They sound so cool. They give such great pictures. They give you great things that you can explain. But the danger in them is that you can easily get another group of people out of it that don't need to be there. Right. So if you're doing a mixture Roche model, don't. No, I don't mind that. If you're doing exploratory analysis with mixtures, be very concerned about extracting data. Now, my paper was not the only one of this. There's a ton of papers. There's some great work by Dan Bauer and Patrick Curran at North Carolina that looked at this about 10 years ago as well. My paper was about 5 years ago. We cited them. They certainly influenced it. But they were looking at mixture models with, I think, factor mixtures and so forth. And it's the same type of business. If any of the assumptions that go into your model don't fit, the mixture model pops out another class. Probably shouldn't be there. So, that's mixture models. Questions? How many of you are currently doing mixture models? You've identified yourself. Anybody else? Not yet. Some of you will. The other thing I was going to mention, in wrapping up, we didn't talk much about classification. I want to mention a couple things about that. Basically, it's clustering backwards. Classification, if you're into it, discriminant analysis will work. It's like MANOVA rewired. So basically, if you had MANOVA, the discriminant analysis is a way of putting people into classes that you know. So if you have a multivariate analysis of variance, you have multiple groups of people, all with a series of observations. You can get a mean vector and covariance matrix for each. It uses the math behind the multivariate normal to go figure out a linear discriminant function to, once you plug in your data, figure out which group a person's closest to with their data. That shows up. The more modern version of this finite mixture models. I didn't talk about those a lot because, honestly, the times, they work very badly most of the time. The linear discriminant analysis is pretty self-explanatory. You can pick it up. I just wanted to give you that label for it. If you're looking for it, it's linear discriminant analysis. It's been around since like the 1920s, 1930s. It's out there. There's people still doing work in it, but its basic premise is that. The mixture models still do it. And I will say the neat thing about the mixture models, the linear discriminant analysis is really the MANOVA approach. If you're a mixture model person, if you know, I told you every one of your models we ran this year we could have done mixtures with. That mixture model approach can do essentially what discriminant analysis does in terms of classification with any model you come up with. So maybe you have a factor model, a factor mixture model, right, where you did multiple factor structures for groups. You didn't collect the group of some new people, put it in, and it will work. It will classify for you. So you can trick out the mixture models to work in that way as well. Okay. And finally, the last thing I get to say is a pitch for my class next year. Enroll or don't, diagnostic testing. Some of you don't enroll. No, there I am again, sinking my teaching. Actually, you're all welcome to enroll. I do like you. I'm sort of trying to play up the adversarial comments, particularly after asking you about quizzes last week. But it does mixture models that are confirmatory, which are supposed to be better, but we'll see that they're not always that way either. So, on that note, I am done, but I need to give you something, which are the teaching ratings, unless you've already